All right, welcome back. So today we are going to look into volume 3 of the textbook, University Physics. So we'll be starting from chapter 1 on the nature of the light, okay? So first, let's talk about the propagation of light and its early measurements for the speed of the light. So the light propagates in the same media in a straight line. So basically, so it was a couple hundred years ago that people tried to measure the speed of light. So the first attempt was by Romeo, and he uses the one of the moons of the Jupiter called Io. So he is measuring the period of Io as the Earth is going away from Jupiter versus comparing to when the Earth is going towards the Jupiter. So you'll see for the light to travel from Io to the Earth, it takes some time, right? And then when we are going away, so then the time for the light to travel will be longer than if we are approaching the Jupiter, right? So taking the difference of the path here and divide by the period, so then we can calculate the speed of light as it travels from Io to the Earth. Okay, so that was determined to be 2.0 times 10 to the 8th meters per second, which is only 33% below the accepted value today. Later, Fiesel had this apparatus constructed, so light comes out from light source, hit this splitter here, and then goes through this rotating teeth, being focused by these two lenses, and then hit on the plane mirror, comes back, and then if it goes through this next teeth here, then you'll be able to see the image over here. So by turning the speed of this guy, you'll know how much time it takes from the light pass through this teeth and comes back over here. So that was for the speed of light for this apparatus was determined to be 3.15 times 10 to the 8th meters per second, which is only 5% off of the accepted value of 3 times 10 to the 8th, okay? There was also the modification of apparatus by another French physicist, so which he measured this guy to be 2.99, much closer to the 3.0 times 10 to the 8th, okay? Theoretically, we knew that you can calculate speed of light from the Maxwell's equation. So 1 over square root of epsilon naught divided by mu naught to be 299, 792, 458 meters per second, which is 0 0.998, okay, times 10 to the 8th. You might also have heard about a light year. So this is not a unit to measure time, but it's a unit to measure the distance the light travel in 1 year. So speed of light times the seconds in the year gives you 9.46 times 10 to the 15 meters. Okay, so that's a very large distance. All right, so when light speed in the vacuum, it has the speed of light, where you see, okay, that's a constant. So it's one of the fundamental constants for physics. So we use that as c. When light speed in medium, we use the speed as just normal v. So the ratio of speed of light in vacuum divided by the ratio of speed of light in medium gives you the index of refraction for the medium. Okay, so and then this is referring to transparent media, so like water, air, or glass, etc. And if you are looking for, if you can calculate this index refraction, you can come to an index refraction table, and then you should be able to identify the substance. On the other way around, if you know the substance, you'll be able to find its index of refraction. So for gases, it's very much pretty close to 1. For liquids, they are a little bit larger. For solid, they are most of them are also larger than liquid. Okay, so in that order. All right. So the light travels in medians, in the same median, in a straight line. So we use the word ray to describe that. So a lot of times you'll be relying on the geometries. So in this chapter, we'll call this as geometric optics in that sense. Okay. It changes direction when it hits another material, interact with the material, okay, in that sense. All right, so light comes from the sun, hits the air's and the Earth's atmosphere, and then it changes direction slightly, and then hits the surface of the Earth, and then get reflected or enters the water, refracted or enters the glass here, and reflected like that. So then its direction of propagation will change. Otherwise, it will stay as the straight line. Okay. Next section, let's take a look on the law of reflection. So this is really a simple law that we have studied in lab. So basically it says incident angle equal to the reflect angle. Okay, for the instant ray, the angle it makes with the normal direction on the surface should be equal to the angle it makes with the reflected ray makes with the normal direction. So theta r equal to theta I. So law of reflection. When the ray hits on the surface, if the surface is flat, if you have multiple rays hit on the surface, then the reflected rays will come out in the same direction. So such a reflection is called specular reflection. So a mirror, plane mirror, will have a specular reflection. Okay. And when the surface is not as flat, then the rays coming at the same angle, they reflected out, not necessarily at the same direction. This is called diffuse reflection. Okay, so if you are in the darkness, if you're shining on the light on paper, the paper is not as flat as the mirror, plane mirror. So you'll be able to see the portion of the paper that's being shined on at different angles. But for the mirror, you'll be not able to see that at all angles. So only a specific angle you'll see the portion of the mirror. Okay, but at the other end, you will not be able to see that. Now, thanks to the most of the surface being not flat, so we can see the surface of the object from different angles. If they are very flat, you'll not be able to see them at certain angle, depending on at what angle the light is shining on it. Okay. All right. When you are looking into your mirror, you'll see your image, right? So this is from geometry here. So the fact you can see, say, a part of your body in the mirror, let's say your foot in the mirror, right? It's because the ray comes off the foot, hit on the mirror here, and get reflected. So the reflected ray comes into your eye. So then you see your foot in the mirror, the image in the mirror. So instant angle should be equal to reflect angle, right? So from geometry here, you see if you extend the mirror down here, so then these two angles are the same, okay? So this angle and this angle is the same, this angle and this is the same. So if you draw a line here, vertical line here, and the triangle here, and then the other side should be the similar triangles, okay? So then distance to the mirror and then distance to the image should be the same, okay? And you also see your image upward because on the top here, you'll see the hair also on the top in the mirror. But you'll see when you raise your right hand, you'll see your image appear to be like raising its left hand in that sense. All right, so the three main properties of prime mirror, image produced by prime mirror. So the first, the mirror is upright, the image is upright, okay, but appears reverse right to left. A mirror image appears to be the same distance behind the mirror that the object is in front of the mirror, and the image is the same size as the object. Okay, so those are the three main characters or properties of image produced by plane mirror. Let's take a look on this example here. It says you stand 1.5 meters in front of a wall and gaze down at a small vertical mirror mounted on it. In this mirror, you see reflection of your shoes. If your eyes are 1.85 meters above your feet, through what angle should the mirror be tilted for you to see your eyes reflected in the mirror? So let's take a look. So when we are in geometric optics, a lot has to do with geometry, okay, and a little bit of trigonometry. So in this case, we need to draw the geometry carefully. Let's say this is the floor you are standing on, and then there's this wall. Okay, on the wall, you have a small piece of mirror. So you are standing over there. Somewhere there, your shoe, okay. And also another shoe there, okay. It's a terrible drawing, but you see the point. Okay, so when you can see your shoe in the mirror, that's because a ray comes off from your shoe, okay, hit on the mirror here, and normal direction of this case, and it get reflected and then hit on your eye. So then it appears to be coming off from your image behind the mirror. Okay, so your image then will be somewhere here. Okay, I probably will not be able to draw a identical image as the object in front of the mirror, but that's the idea. Okay, so in this case, so this angle will be theta. This will be also be theta because reflection, right? So normal direction, this is vertical, so then this is horizontal. So this guy will be also theta, okay? Now let's see, mirror is small, so if your light comes off from your eye right here, it will be shining on here and then it will get reflected in this direction. So the reflected ray will not come into your eye, so you will not be able to see it. So you have to tweak this guy a little bit, okay? So in order for you to see the ray has to come back, okay? So that means this angle and it comes in, comes right back, right? So the light ray goes in, goes back, so that means it should be the normal direction. So you have to tweak it, tilt it in the mirror to be like somewhere there. So this is the normal direction. So it looks like you're actually looking for this angle, right? You need to tweak the or tilt the normal direction of this guy to that degree theta. So you're looking for theta, basically. Okay, so from your geometry, you're looking for theta. Okay, now let's take a look on the numbers given. It says you are standing 1.5 meters away, right? Now, according to the property of your image in the mirror, it should be also 1.5 meters behind. And it says here from your eyes to the foot is 1.85 meters. Okay, so if we look at this big triangle here, this should be a 90-degree angle. Then this is the angle theta, which is the same as that one. So opposite over this guy, right, gives you tangent. So tangent of theta equals to the 1.85 meters over 1.5 plus 1.5. Okay, so 1.5 plus 1.5, which is 3. So then theta will be equal to tangent inverse of 1.5 over 3. Okay, that gives you 31.7 degrees. Okay, so that's the angle you need to tilt your mirror. Okay, so in order for you to see the image of your eye in the mirror. Okay, so let's go back to the PowerPoint slide. If you have a couple of the prime mirror, you can put them perpendicular to each other, okay? So then the light rays strike on the mirror will get reflected 1 time and 2 times and then coming out. So the fact that if you have those two perpendicular to each other, light ray comes in, will comes out parallel to this initial direction, okay? So an apparatus like this is called corner reflector or retro reflector. Okay, so that's because this instant angle, right, should be equal to this reflected angle, and this instant angle should be equal to that guy. Now this is 90 degree, so this angle equal to this guy, this angle equal to that guy because this is parallel to that guy. Okay, this is parallel to this. So these two then will add up to be 90 because these two will add up to be 90. Okay, now this is half of this whole thing. This is also half of this whole thing. So that means this angle plus this angle is 180. So these two add up to 180. That means these two are parallel to each other. Okay. And if you have three parameters, you can also make a corner reflector like that. So the instance angle hit down here, get reflected and get reflected again, get reflected backward. So this also will be parallel to the instant. Okay, so you can work on the geometry. You should be able to figure that out. Okay. All right. Let's move on. Take a look at the reflection. So when the light hit the surface, if this surface or medium is transparent, then part of it will be reflected still. Part of the light ray will get refracted and enters the media. Okay, so then that's what happens like this. Okay, so all here. So this guy hits here, get reflected. Also on this side, get reflected. Okay, so that sometimes can create um, not real images or creates you like images more than you normally would think. So if there's a fish there, you actually see kind of there are three fish there, but there are actually only just one there. Okay, we'll take a look on this. So when the light hits the surface, the transparent medium reflected. Also, this should be you can imagine should be reflected partially, and then the other part should enter the media. Okay, so for this, it obeys the Snell's law, which is called the law of refraction. N1 sine theta 1 equal to N2 sine theta 2. So N is index of refraction of medium 1 and 2. Angle theta 1 is the instant angle, theta 2 is the refracted angle. Okay, so in that sense. So you can switch the two sides of equation. So that means the light can also enter from second medium into the first medium. Okay, so reverse way, pathway is also true in that sense. Okay. Snell's law can be written in terms of the angles as well as the speed as well, because the speed of the light in the median is associated with the index of refraction, so inversely proportional to each other. Okay, so then it can be written as sine of theta 1 over v1 equal to sine of theta 2 over v2 in that sense. The basic properties of the refraction of light. So when the ray of light enters the media where its speed decreases, it bends towards the normal, which can be seen from this equation. So if speed decreases, right? So which means speed smaller, theta angle will be smaller. Okay. So if V1 is or V2 is less than V1, then theta 2 will be less than theta 1. So then it comes in at a certain angle, but then angle theta 2 will be smaller. That means closer to the normal line. Okay, so bend it towards the normal line. The other way around will be true. If the speed increases, then it bends it away from the normal line because angle should be bigger in that sense. If there's no change in the direction of propagation, then there's no change of index of refraction. Okay, if the two are the same, then you don't have that. The greater the change in the index of refraction, the greater the change in the propagation direction. So that means the angle, changing angle will be greater. Okay. In a ray of light goes from one medium to another along the normal, it's deflected. So that means if your instant angle is the instant passes along normal, that means the instant angle is 0, right? So the x angle should be also 0 in that sense, according to Snell's law, because n1 sine of 0 is equal to n2 sine of 0. All right, and so refraction of light can sometimes give you false impression, right? So if you see a pencil immersed into water, you'll see like it appears to be bended. So similar, like if you have straw into your drink, right, you'll see it bended. So the fact that that's the case is because you can take a look on one point of the pencil here, and out of this point comes out two rays, right? Both hit on the surface, get refracted, and then they come into your eye, but they appear to be coming from a point over here, which is higher than that. So then this guy appear to be bended. Okay. Also, in the summer, particularly, if you look at the surface of the ground, it could be hot. So then above there should be cooler. So there's a temperature gradient here, which makes a variation of density of air also that is related to the intense index of refraction of air. So index of refraction varies. So then a light ray comes from here will be bended because it's being reflected constantly and then curved and then comes to your eye, but it appears to be coming from somewhere down there. Okay, so then you see an image of the object from the above the ground to be like that. Or if you are driving down the road, you'll see probably like the clouds in the on the low surface, the image there. Okay, so those are called mirages. Okay, take a look on this example here. It says scuba diver submerged into the water and looking up in towards the calm surface of the freshwater lake and notes that the sun appears to be 35 degrees from the vertical. The diver's friend is standing on the shore of the lake. At what angle above the horizon does the friend see the sun? Use the index refraction of water for 1.33. Okay, so let's take a look. So let's say this is the calm surface of water of the lake, and then it's the normal direction when a scuba diver looks up, right? So a ray from the sun enters his eye. One eye will be enough, okay? So, and the sun ray probably comes from somewhere here, okay? So it says this is 35 degrees. It's asking you if a friend on the shore looks up, right? So then they are looking for this angle. All right. So let's call this as theta 1. This is theta, all the other way around. Theta 2 here. This is theta 1. Okay. So then we are looking for this theta. So this should be 90 minus theta 1. Okay. So we need to look for theta 1 first. So you apply Snell's law, n1 sine theta 1 equals to n2 sine of theta 2. Okay. n1 is 1.0003 sine of theta 1 equals to n2 1.33 sine of 35 degrees. Okay, solve for theta 1. Theta 1 equal to sine inverse, okay, of both sides divided by the almost 1. Okay, that gives you 49.9 degrees. So then theta is 90 minus 49.9, which is about 40 degrees. Okay. So let's go back to the slide. So next, let's take a look on the total internal refraction. Okay. So when the light ray goes from a higher index of refraction media to a thinner or smaller index of refraction media. So for example, water and air. Okay. So you can see sine theta 1 and equal to n1 sine theta 1 equal to n2 sine theta 2. Okay. So because n1 is greater than n2, so then this guy has to be greater than this one, right? Greater number times smaller number equals to smaller number times greater number in that sense. Okay. So as you can see, theta 1 is less than theta 2 then in this case. So you can increase your theta 1, right? So at one point, theta 2 will reach 90 degree, right? So then the angle for theta 1 is called the critical angle. Okay, so I think it's not this guy. Okay, it will be this guy, theta 1 here. At this point, it's the critical angle. So when that happens, then you can keep increasing theta 1, but then refraction will no longer happen. Okay, so then you'll just have this ray comes in here and get totally refracted. Okay, so no light will come through into the second media. Okay, so this is what happens. So you can calculate what will be the critical angle by setting theta 2 equal to 90. Okay, so then this guy equal to 1 because sine of 90 is 1. So n1 sine theta 1 equal to n2 then. So solve for the angle that gives you theta. So the angle theta 1 will be your critical angle theta C, okay, which is sine inverse of n2 minus n or over n1. Okay, in the case of n1 is greater than n2. All right, let's take a look on this example here. So it says you can determine the index of refraction of substance by determining its critical angle. What's the index of refraction of a substance that has a critical angle of 68.4 degrees when submerged in water? And what's the substance based on table 1.1? What would be the critical angle for this substance in air? Okay, so we'll take a look on this one. So you have this substance in water. So that means the substance and water on top. Okay, we know water has 1.33 as an index refraction. So we're looking for this guy. We can call it N1, N2. So let's call this N1 here, and then water to be N2 because it goes from the substance to the water. Okay, so this guy. And when that happens, total internal refraction happens. So theta 2 is 90. And it tells you theta 1 is 68.4. So we can apply Snell's law, N1 sine theta 1 equals to N2 sine of theta 2, be 90 degree. So, and you can find N1. N1 should be equal to just N2, because this is 1, over sine of theta 1. Okay, so 1.33 over sine of 68.4 degree. That gives you 1.434. All right. And you look at this up in the textbook of table 1.1, this tells you this is fluoride. Okay, so that's the substance. Now B is asking you what would be angle critical angle if this is air instead of water. So again, this theta 2 should be equal to 90 degree, but this time the angle theta 1, it goes up there. That's what you're looking for. So you apply this again, sine of 90, okay? Given now N2 is 1.0003. So that's 1. Sine of theta 1 is equal to N2 over N1. Theta 1 is sine inverse of N2 over N1, where N2 is 1.003, N1 is 1.434, sine inverse, okay? So that gives you 44.2 degrees. All right. Okay, so we'll go back to the slide. Now we'll take a look on the application of the internal refraction. Okay, so the first is for the application for the object in the binoculars. Okay, so when the light comes in here, it goes to these two, total internal refraction, okay, and then comes to your eye. And because of total internal refraction, the intensity of the light will not be reduced because it will be all contained. Okay, the same as for the fiber optics as signal transportation. So then it comes here, refract the total internal refraction. So intensity comes in should be equal to intensity comes out, okay? Instead of being leaked from the side walls in that sense. All right, I guess we'll stop here for today, then we'll come back another time, okay? See you guys, bye.